Okay, now that we have learned about linear regression and logistic regression, and we've seen some simple examples, we're going to now do it for real. We're going to use our insurance data set again, and this time we're going to use logistic regression to predict the probability that someone is going to crash their car. So we're going to build off of the code that was written in previous lectures where we first developed a decision tree, then we developed a random forest, and then we built a gradient boosting model. So we built those three models, and now we're going to build a logistic regression model, and we're going to use forward selection. We're going to do a forward stepwise selection here, and then we're going to use our decision trees to select our variables. So we're going to do two different logistic models. So we'll start off with reading in the libraries that we will need. Let's get those guys read in. Okay, and so those ones have been read in. And again, sometimes you will get a warning message that your library might have been built under a previous version of R. That's not anything to worry about. It's just saying, hey, at some point you might want to consider updating this. And then you would just go up here and reinstall it. But that's not going to be a problem. So let's, I also have to load in our gradient boosting model. Let's load that guy in too. And there we go. So let us start off by reading in the insurance data. And if I do head df, this gives us the first 6 records of the insurance data set. And if you recall, this data had previously been scrubbed so that there's not any missing values. Also, our categorical data, such as whether or not your job, for example, which is a categorical variable, we have converted those into flags. So are you a doctor? Yes or no. It's a 1 or a 0. Are you a blue collar worker? A 1 or a 0. So this data has already been scrubbed. We don't have to worry about that. And we can, it's usually a best practice just to do a quick summary of the data to make sure everything is copacetic here. Let's see. And we don't, if we just take a quick look at the summary, I look for any there should be right underneath the max value here that would indicate if you have any missing values. And I don't see any, and I don't expect to see any because I know we've fixed this data already. Okay, so now let us break our data into a training and a test set. So now we have a training data set. So we took our data frame here and we have broken it into a training data set. And then we've also have a test data set. So we're going to build our models on the training data and we're going to test it on our test data. So if our model is any good, it should be able to perform well on data that it's never seen before. So let's just take a quick look at the dimensions of this data. And you can see that all of the data has 10,000 rows and 46 columns. Our training data has 7,171 rows, and our test has 3131. So if we add these two guys together, we should get 10,302. So now we'll start by building a decision tree. And let's take a quick look at that. So this is a tree. We've already done this before, but let's build this decision tree here. And we have this decision tree, and it also is giving us the important variables too. So we have a tree. This is what it is right here. And it says here that people who live in the country don't crash their cars. People who have salaried jobs, doctors, lawyers, they don't drive as much, so therefore they don't crash their cars. People with expensive homes, that's more of a surrogate for people who, well, actually, looks like here that valuable houses do crash their cars. Look at that, 35%. Interesting. Has your license ever been revoked? If it has, you really crash your car. So there's, you can look at this stuff and figure if this makes sense or not. But the point is we have a decision tree. And we also know what variables the decision tree considers to be important. So now we will predict on the test data, we're going to predict the chances that you are going to crash your car. And we're going to get ready to do a rock curve there. So this is the predictions, and you can see that the probability of the first few people. And also, if we want to do a rock curve, we're going to need this here, this true positive rate and false positive rate. This is, if you recall from previous lectures, this is what we're going to need to build our rock curve, and we'll use that shortly. Now, we're also going to build a random forest. And that will also give us the variable importance. But let's just run this thing. Now this will take a little bit of time to run. So as it runs, I may put us on pause while it's running. So it might take a few minutes. So it's beginning to build the random forest, and I'm going to put this on pause so we don't have to sit here and listen to awkward silence as the random forest is running. And we are back, and so the random forest is complete, and we also have a list of the variables that it considers to be important. And now we're going to do the gradient boosting model. I believe this one runs relatively quick. And I might pause for, no, this one's done. Yeah, the gradient boosting was a very fast one to run. So, okay, and so we have its variables that the gradient boosting likes. And now we're going to move on to our logistic regression. So now we have a tree, a random forest, and a gradient boosting. Now we're going to build a logistic regression, and we're going to use forward selection here. And the reason why we're going to use forward is there's a lot of variables, and if I did stepwise going forward and backward, it might take a long time to run. It's not that that's a problem, but I'm just decided I'm going to use forward selection here. So in order to do this, we first need to have an upper boundary, and this will be all of the variables that we will use at most. And in this case, I've decided we're going to use all of them. So on the upper level, we could conceivably use every single variable. So we're going to build a model with every single variable. That will just take a moment. And there we go. It's built that model. And now we're going to build another model that has no variables in it, just taking the average. So we have an upper and a lower boundary. Now we can do a summary of them if we wish. And we can say, well, the upper boundary using all of the variables. And this is a huge mathematical formula that we could use. And it's overly complicated. And over here is an overly simple model, which just simply says, okay, I don't know how, you know, I'm not even going to use any variables. I'm just going to take an average. So that doesn't even use any variables. So now we're going to do a stepwise selection from the lower level, starting with nothing. We're going to do a forward selection. We're going to add variables one at a time, and we're going to go from nothing, and it could go as high as everything, and it's going to stop when it starts improving. So let's run this guy real fast and see which is the best model. So we start running this thing. And actually, I'm not going to stop. I'm just going to run this thing step by step. So now he's got 3 variables, 4 variables, 5, 6, 7. He keeps adding. And if you notice this AIC value, 66, 81, 29, it keeps going down because if you recall AIC, the smaller the AIC value, the better the model. So this thing keeps adding variables and it keeps improving the model, but obviously AIC punishes or penalizes you for a complex model. So when we add variables, they're doing good in spite of the fact that we are making the model more complex. So this is the model that is the ideal model. So we have all of these variables. And let's just summarize that model. Okay, and there we go. These are all of the variables that we're using to determine whether or not you are going to crash your car. And the positive values mean that you are more likely to crash your car, and negative ones mean that you are less likely to crash your car. So you can see that, for example, doctors, because they have a negative sign, are very unlikely to crash their car. Managers are very unlikely to crash your car. This is probably indicative of the fact that you don't drive as much. And then you have people who've had their license revoked, probably from drunk driving, has a very high positive number. That number is probably indicative of the fact that, you know, if you've driven while under the influence of alcohol in the past, you're more likely to do it and you're going to crash your car. Same thing over here with this person here. MVR points. That's how many times have you gotten traffic tickets. If you speed in the past, you're going to speed in the future, and you're going to crash your car. So this looks pretty good. Let's build a ROC curve using only this data. I just want to see what this ROC curve looks like. And let's take a look at what it. So there, that's a nice looking ROC curve, nice smooth ROC curve, nice bow to it. And this is our ROC curve of logistic regression using forward selection. Now, for fun, we're going to use the decision trees to help us develop a predictive model. Now, I could just use that, but I'm going to make it a little bit more complicated. Let's start off with finding out what are the variables that the decision tree likes. So if I run this command, because remember, we've already built this model, tree model, way back up here. Say we built this tree model already. So I'm going to use this guy again, and I'm going to say, hey, tell me, Mr. Decision Tree, what are the important variables? And if we do that, and I do tree vars, those are all the important variables, and it gives us a level of importance. The higher the number, the more important the tree considers it to be. Well, I don't want these guys here. I just want the names. So let's get that. And the way to get the names is just type names of these guys. So let's try that again. Tree vars. That's a lot of names there. Now, what I could do is I could start typing in these names one at a time with a plus sign in there. So I could say that the formula is, you know, target is equal to flag urban plus flag job salary plus dot dot dot. I can do that. That would take me a long time to type this. I'll probably make a mistake. And if I had 100 variables, that could really be not fun. So now I'm going to teach you a shortcut to do this the easy way. Well, the first thing we do is we've got these tree variables right here, right? Now watch what we do. We're going to use this command here, paste. So we're going to take those tree variables and we're going to paste a plus sign in between each one of them. So watch this, tree variables plus, and we're going to paste the tree variables and a plus sign in the middle. So let's do that. Whoops, I don't think I got, let's do that. Tree vars plus. Look at that. So now I've got flag urban plus flag job salary plus. So look, I got the whole, all the variables are input with a plus sign in. Okay, now all I need to do is tell R that this is a formula, and we want R to paste our target, which is target claim flag, and then a little squiggle guy there, and our plus signs. So, and then it's and we're also telling R that this is a formula. So let's do that. And there, if we type F, look at that. We've got a formula. The claim flag, blah, blah, blah. So this is a formula that uses all of the variables that the decision tree liked. And it's stored in the variable F. So now I can do GLM F, and F is our formula. It's a binomial. And we're going to build it with this train data. Now we could just use this right now. Now if I did a summary of this, let's tree logistic regression. And now this will tell us the variables that are, the decision tree used, and this is now those same variables were put into a logistic regression. Now let us go over here, and we're also going to say the lower boundary. The lower boundary will be just no variables at all. So let's set that one again and paste it in here. And if we do a summary of the lower boundary, logistic regression, there we go. So we don't have any variables in that model. So, well, I've got the summary commands already written there. So now I'm going to do a stepwise selection because there's not a lot of variables there. So I decide I'm going to go in both directions. And I'm going to start with the lower boundary, meaning I got absolutely nothing. I'm going to go in both directions, and I'm going to go from absolutely nothing to at most the variables that the decision tree liked. So let's try to do that. So we're going to use decision tree to help us decide what are the most important variables. So let's do that. And there we go. So now we have, these are the variables that were ultimately used in the decision tree. I mean, in the stepwise selection, where the decision tree helped us prune down to a smaller amount. And this is incidentally a technique that's often used in the corporate world. If you have, let's say, 10,000 variables, and that's not an unreasonable thing to expect in a large corporation, you might have something like that. You don't want to do a stepwise or a forward selection on 10,000 variables. So you would use a decision tree, and you might get the number down to, let's say, 50 variables. And then you can find using a stepwise selection to get a better model. There's no guarantee that this will be a better model, but it certainly is a good technique to try always. And it might work. Sometimes it doesn't work as well. So let's find out. Let's do our rock curve here. And see, well, that's another nice rock curve. How about if we superimpose all of them at the same time? So we come down here and we're going to plot the tree. So PT3 was the tree, R was the random forest, G was the gradient boosting. This was the logistic regression using stepwise, and this is our logistic regression using the tree and stepwise. So let's plot all of these guys and see what we get. And let's take a quick look here. The tree, in this case, didn't do as well as everybody else. This was the tree and stepwise selection at the same time. And it did not do as well as some of the other ones. This gold one here was our logistic regression using forward selection, and the red and the blue were the random forest and the gradient boosting. So the random forest and the gradient boosting did the best here, and that's usually to be expected. Those tend to do very well. But in my opinion, the logistic regression using forward didn't do all that bad. So I might still go with the logistic regression because of the logistic regression, even though it's not as good, it's easy to explain. If a regulator comes in and says, let me see your model and explain to me why you are not violating any laws, I can point to a mathematical formula and show that I'm not doing anything, dishonest or unethical or, negligent. And it's an easy thing to explain. So I might go with that one, depending on the situation. Just for fun, let's also look at the rock, or the area under the rock curve. And then, again, the perfect score would be 100%. And let's see how each one of these performed. So the decision tree had a 72%. The random forest was 81. Gradient boosting was 81. Our logistic regression was 80. And our logistic regression with the decision tree was 78. So this guy it was pretty close to these guys. So I might go with, in my opinion, I would go with this guy right here, the logistic regression using stepwise. Now, again, the lesson here is that you never know what model is going to be the best. If we ran all of these models with different data, somebody else might win. So it's always a good idea to try many different techniques and then see which one is the best. And then if you have several which are the best, one is maybe, like in this case, the top three here was random forest, gradient boosting, and logistic regression forward selection. In that case, if they're all close to one another, I might take the easiest one to explain or the easiest one to put into production or something like that. I can use other factors as well. It doesn't necessarily always need to be the most accurate. So anyways, this is our example of using logistic regression, and we used two different techniques of variable selection.